YouTube's running. Blackboard Collaborate is running. Spiros left. Spiros is coming in. Hello, Spiros. And we've got Jason coming in as well. Hello. Right, I can't hear anyone at the moment. Your microphone will be muted by default, which is probably a good thing. We don't want hundreds of microphones all blaring out at everyone. But if you want to say something, by all means, unmute it. I need to quickly type those up, don't I? Right. Right, manners, what else? Then we've got, haha, yep. Not much else we can do here, really. Would have been nice if we could go back into uni and I could see you all in person, but unfortunately, coronavirus is still having its taking its toll around the world. Right, microphones. Keep them muted unless you're asking a question. That should be pretty much it. Right. And have we got a few more? Yes, we've got Jason and Kevin in the room now. That's good. Is that the third year one? Yes, I believe that's the third year one. 4 years, no one. Maybe. Yeah, now I tried this, like, just to check that everything was working. I did try this with my brother, and obviously the first thing he did was try to draw a phallus on the board. So I think I should probably make that very clear that I don't want them drawn. um, good to rephrase that. That's better. Right. And I will paste those in the chat as well. And we have Han in the 4th year chat. That's good. It's a shame I can't merge these two streams, to be honest. But there we go. Doesn't seem to have an option to pin a particular message, which is annoying. Oh well. Right. Haven't got any raised hands either. Good. Right. Right. Have we got any? Share with me? No, there isn't. It's not on here anyway. Shared. I'm just going to check this one out because if none of these are beyond the current date. Yeah, I don't think I've got any that's beyond the current date for Lab 2, in which case I can load up X to go and show you something. Right, that one. Layout. So we'll get there in a minute. Alright, thought a few of you might be interested in seeing this, so I thought I'd bring it up. So, as far as I can tell, the minimum size you can make for your OR2, like the absolute minimum that anyone could get, would be 7 wide by 7.9 high. So we see the... you can't see the text on here because it doesn't zoom text, but the width across the ground rail at the bottom I've got is 7 microns, and from the bottom of the ground rail to the top of VDD is 7. Right? So this is the absolute minimal sizing you can get for Lab 2 if you want to try and manage that. But you don't have to get this to get high marks. Like, I wouldn't expect many people to create the separate NDIF via over here and then remove all the substrate contacts from their PMOS transistors. So, like, it is possible to do this, but you don't have to do this, right? But that is the absolute minimal that can be achieved. So if you got anywhere close to that, that's great. For a first attempt, let's create another layout and just sort of make one very, very quickly. Cell view, we're going to call it, right, it's going to be this layout gone, and we're going to call it layout 2. Okay. Let's see what happens. We try and give it a quick one. So, connectivity, create. No, it's because I opened this wrong. That's why. So go back to the schematic, which I've got down here somewhere. Launch. Layout Excel. Create new automatic. I'm going to call it layout 2. Okay. And we'll see what we end up with. When Cadence decides to respond to me. Yep, right, okay. There we go. Connectivity, generate, all from source. Opens, met one pin, create label as. Come on. Pin, metal 1. Okay. Right, connectivity, generate, places in schematics. Okay. Shift F that. Press F. Right, so for a very first attempt, what I would expect you to do probably is to get this one entirely the wrong unit. Click down there. Shift O, click down there. So I'd expect you to just go like that to get those two to merge, because that's a very easy thing to do. Substrate contact on that one. Then this one would probably end up on its own with its own substrate contact. I would probably, so that one will need to rotate to 1 unit. Rotate that one. I want it to be rotated that many degrees. Or shift over that again, around 180. Let's line those two up. Let's just sort of make them somewhat adjacent. And then with these lots, I probably would have expected you to rotate this unit again. That way. Actually, no. That way. This one should go. The source needs to go over there, so that should be there. These are the two ones, A and B. A and B like. Swap these two round again because they're around the wrong way. Shift O. Like that. There we go, simple merge of those two. bit. Add a substrate contact to him. And then suppose connect them up. Need to create my rectangle for my metal one. That tool. 1.0. Right. So for your first attempt, if you did something like that, and then move that somewhere down there. Put this one, right, this one should be connected to here, so I'm going to pop it down there. And the out will be somewhere over here. Right, so if I just do a rough estimate of how tall, if you can get, say, 10 by, if you can get 100 microns, that would be a good estimate of your, like, a good first attempt, right? So yeah, if you can get 10 by 10, that will be a good first attempt, just to give you an idea. And then, like, maybe that will give you 50 like 50% of the marks for that. And then if you get down to the 7.9 by 7, which is like 55 point something, that would give you up to like the 100 marks for it. Okay, those are just like rough numbers. That's just, here's a rough estimate of whereabouts it'd be. Okay, right. Jodeep has asked, can you explain the exact sizing considerations in exercise 5.1, because you mentioned that we need to size to obtain the same high to low and low to high propagation delay, but that cannot be done with minimum size NMOS, PMOS and NMOS in the inverter. Right, okay. In that case, I am going to share a whiteboard with you. Whiteboards, there he is.
Hello, Scott.
Oh, hello, Varun.
For the minimum, the least area, can you show how the layout looks like?
Oh,
For the
for the minimum, yeah, I'll just pop back to that for a quick moment. So that's the absolute sort of minimal configuration you could get, as far as I can tell. There is, you can shave off like 25, 50 nanometers if you really want to compress this mess over here. There is a few nanometers you can shave off again. However, given that the auto router wants your cell width to be a multiple of 1.4, the fact that this is currently at 7, which is a multiple of 1.4, is very helpful. So it would be better to leave it like this rather than trying to compress it that slight bit more. Okay, so that's why I say that the best configuration is 7 wide by 7.9 high. But in order to achieve that, you have to really understand what a body contact is for, and understand that you can completely and utterly miss out the body contacts on the top 3 PMOSs, and instead create a custom via from the metal layer connected to VDD down to an NDIF, which will then tie your body of your substrate to VDD, allowing your PMOS transistors to work correctly without going into the properties on one of these and enabling a substrate contact. Okay, so you can only
okay.
do it if you understand that.
What are these two leftmost um, on the top left corner? These two contacts,
Yep,
VDD and VDD. What is that?
this one here.
Down? Yeah, yeah.
Right, so this is the custom NDIF via that you would need to do in order to get the width down to 7. If you don't,
Oh,
then you need to have this transistor here the A transistor needs to have a substrate contact on, meaning that you can't merge
Yeah.
it with the inverter PMOS. Okay, so
Okay.
putting it back to, if I go back to the schematic, what we've done is rather than having a custom, a normal body contact on this transistor here,
Okay.
we've said we'll put a body contact somewhere else, and then we'll merge the source regions of these two. Okay? Right. So yeah, that's what these two contacts here are doing, really. So we've got an NDIF region here, plus the
Okay.
diffusion, plus the metal layer and the vias, which then ties the N well all round here down to up to VDD.
Okay.
Okay, right,
All right. Thank you.
right. Right. Of lab 3 for the minimum size inverter. Right, okay. Spiros, I'll get back to your question in a sec. I need to answer this one from Joydeep first. Right, so with exercise, so looking at exercise 5.1, question 1, right? What it says is that you need to create a custom implementation of Y, right? Such that, right, TPD HL of Y, so the high to low propagation delay, equals TPD HL of the minimum sized inverter, right? Or actually, I'm actually going to denote that slightly differently. I'm going to call it inverter 1, 1. So both the NMOS and the PMOS have got minimum width. Okay, so inv11, inverter with a minimum sized PMOS and a minimum sized NMOS, right? Normally, our minimum sized inverter is going to be equal to inv 2, 1, right? Normally we do that due to the difference in electron hole mobility. However, what we want is we want our custom size 1, so y, x, y, yeah, x and y, let's call it, y, x, y, so that, I'll just remove that. We got more parameters in there anyway. So we've got to have our y size such that the propagation delay from high to low is the same as an inverter, and the propagation delay low to high of y is equal to the propagation delay of the inv 1, 1 scenario, right? So if I draw out my inv11, so we've got our input going into our PMOS, then we've got our NMOS down there, connected to our input, there's the out, VDD, ground, in, this is 1U by 0.35 U, this one's 1U by 0.35 U, so this is your inv 1, 1, right? So the resistance here will be R P min, and the resistance here will be R N min. So when you draw your Y, got your A, B, C, and D inputs, right? You've got your Y output, you've got your pull-up network, and your pull-down network. Pull-down network obviously connected to ground, pull-up network connected to VDD, two connected together, and to the Y input. Obviously these are all connected into here, and I'm just going to use red so that you can see they're overlapping, connected into here, right? The resistance of this thing should be Rp min through any one path, and the resistance through here should be Rn min through any one path. Okay? So, when you size your transistors, you need to make sure that the resistance on any path is equivalent to one of those. If I create a new whiteboard, yes, okay. So if we've got, say, so this is looking at your pull-up network, and then we've got something like that. For example, I don't know if that's correct. I'm not even thinking about what the equation here is. And then that's your output, right? Resistance through this path here must be less than or equal to Rp min. But also, resistance through this path must be less than or equal to Rp min. Therefore, we know that, so if we say, look at this path over here, we would say, okay, that should be size 2, that should be size 2, meaning that each of these two will be half of Rp min, and then when you add them together, that will be Rp min, right? Then we could look at this path, and we could say, right, we've got half an Rp min here, so between these two, we need half an Rp min, so we'll make them each a quarter of Rp min. Right? So it's sizing like that. We say, what is the resistance that we want to charge up our output? Make sure any path through it gives us no higher than that particular resistance. Right, if we have made the delay equal to the normal minimum size inverter, how many marks can we expect for that, or would that not warrant any marks? If you have done it for if you've done it for inv 2, 1, so that's your normal minimum size inverter, I will probably, I'll subtract a few marks, but I won't make it particularly high. So what you'll end up with is all these will be double what they should be. So you might end up with 4, 4, 8, 8. And then that will be equivalent to Rp min by 2, Rp min by 2, which will be for the inv 2, 1. If you do that, as I said, you'll lose a few marks for not really reading the question, but you should get most of the marks, because the main part of it is understanding the idea of getting the correct resistance and a balanced resistance through each path. Right. So what does this say? Right, so a question from Spiros. For this example, wouldn't it be better to make the width of all the PMOS to the left 3 instead of 2, 4, 4? Yes, okay, so that's the other thing. Depending on which order you look at these paths in, you'll probably end up with a different solution. Some of those solutions will be better. So for the solution I've got here, the total width of transistors is 4 plus 4 plus 2 plus 2, which equals 8 plus 4, which is 12. If, on the other hand, we looked at this path first, right, we would end up with 3, 3, 3. And then we'd look at these two and we'd say, well, this is Rp min by 3, so this one must be less than or equal to 2 Rp min by 3, and therefore its width would be 3 by 2, right? Or you could say the width is 2 if you want to keep it an integer number. we do it this way round, we get widths of 3 plus 3 plus 3 plus 3 by 2 at the absolute minimum, which is 9 plus 1.5, which equals 10.5. So you get a better result if you look at the longer paths first, right? Because the longer paths are generally the ones that are going to end up doing this, where you've got one transistor taking a small amount, one transistor taking a proportionally larger amount than the others, right? So that's why it's better to look at your longer paths first. Right. Okay. So for exercise 5.1.6 of lab 3, oh Christ, we're already in. Christ, I didn't notice that we were so far in. Okay, we've got a lot more people. Spiros, I will answer your question at the end once once the lecture's over, okay? Right, so, that one. Right, okay. Since it's been a while since we've had a lecture, what I'm going to do is I'm going to start off with a quick revision of sequential logic, what we did on the lecture before we broke up. And then after that, and then I'm going to finish off the last few slides and then we'll see if we've got some time for like some worked examples, right? So, up until now, we've been doing, and I need to change this to a laser pointer. We've been doing combinational logic. Combinational logic, if you remember rightly, is purely dependent on its inputs. It is a pure function, right? If you know what the inputs are at one point in time, you know exactly what the outputs will be. This is only from a functional standpoint, mind you. Obviously, timing is a bit different, but if you just want to know what the outputs of some combinational logic is, all you need to know is what the inputs are at that moment in time, right? However, some of our systems, some of the designs we might want to make, require us to have some form of memory. We want to know what the input was in the past or what the output was in the past. If we want to do that, we can't just use combinational logic. We need sequential logic. We need state registers, right? What our state registers do is they get told what they need to remember by the combinational logic, right? But at the same time, they tell the combinational logic what they have remembered from the most recent time instance. So, for example, with a flip-flop, as we see here, we remember something on the positive edge of the clock, and then that value that we've remembered is available until the next positive edge of the clock, right? So we remember the value that our combinational logic output for a whole clock cycle, right? And the combinational logic can tell us to store whatever it likes, as long as we've got enough memory to do so, okay? And then it's up to the combinational logic to interpret that data correctly, right? We saw that sequential logic, so these state registers, come in two forms, latches and flip-flops. Latches are level sensitive. They say if the clock is high or if the clock is low, depending, it is either transparent or it is opaque. It propagates its value or it holds its value, right? For a positive latch, it propagates its value when the clock is high. For a negative latch, it propagates its value when the clock is low, okay? Flip-flops, on the other hand, are edge-triggered, right? The positive flip-flops become transparent only while we are undergoing a positive edge on our clock. So we're going from 0 to 1 on our clock, and at all other times, they are holding the value. Conversely, the negative flip-flops only become transparent when the clock is undergoing a negative edge, so it's going from 1 to 0. At all other times, they are opaque, they hold their value, right? And we saw that flip-flops are quite often built using a pair of latches, right? So obviously, this edge theoretically it's just one very, very small time instance, right? So we need to define what the timing is on these edges, right? And so we defined the setup time, the hold time, the propagation delay, and the contamination delay. The setup time is the time that the data must be stable before the rising clock edge. In this case, we're looking at a positive flip-flop. And the hold time is the time that the data must be stable after the clock edge. If either of these two times, the setup time or the hold time, is violated, if this data changes around here, then it will corrupt our output. We don't know what our output will do to us, right? Then, once we've held our data stable across the setup and hold time, right? A short time after our clock edge, our output will start to change, like a few bits of it will start to change. And then a bit longer afterwards, we will have the entire output having changed, right? So this is the contamination delay, how long before the output starts changing. And the propagation delay, how long before the output has finished changing, right? Everything is measured, as we do with all our propagation delays, from the 50% points of our signals. So from 50% of the clock to 50% of the output, and from 50% of the data to 50% of the clock, 50% of the clock to 50% of the output. Everything is measured by 50% points, right? But these are the important timing metrics: the setup, the hold, the propagation delay, and the contamination delay, right? And we saw why this is important. We saw that if we have a system like this, where our combinational logic loops back onto our state registers, if our data doesn't get from the output of the state registers through the combinational logic to the input before one setup time before the next clock edge, it will corrupt our data. Similarly, if we have our data get from the output of the state registers through the combinational logic and back to the input before the hold time of that same clock edge has expired, it will again corrupt this value here, right? So we need to make sure that the delay from here back round to here is not too short and not too long. If it is too long, we violate our hold time and we don't get the correct data for the next clock cycle. If it is too short, we corrupt the data for the current clock cycle, right? And so we defined these two equations. So our clock period must be greater than or equal to our propagation delay of our state register plus our propagation delay of our logic. So that's the time to get a valid piece of data from the clock to here, and then through round to here, and then for us to have a full setup time before the clock transitions again. Similarly, for the hold time, we said that the contamination delay from the clock to the output plus the contamination delay through the combinational logic must be greater than or equal to our hold time in order for us to know that the hold time has expired. We saw there was two types of storage. Static storage, which is regenerative. It connects its output to VDD or ground. And you have dynamic storage, which stores a charge on a parasitic capacitor, right? We're focusing mainly on static storage at the moment. We saw the cross-coupled inverters, and we said by looking at our voltage transfer characteristics of our curves and saying, well, if we invert the axes on the second inverter, because we know that VO1 is the same as VI2, and VI1, due to this loopback connection here, is the same as VO2, because they're now on the same axes, we can combine the two traces together, and then we can then use them to analyze what this circuit will do. So if we say that our voltage is currently here, right, on our VI1, we can then look up what our VO1 will be, which is here. And since VO1 is tied to VI2, we can use this value of VI2 to look up VO2. So we can go over and we can look up VO2 to be this value. Then that VO2 is connected back to VI1, so VI1 is now this value, and we can use that to look up VO2, and we see that it pushes itself towards the A state. Conversely, if it was over this side of the C, we would see that it would propagate itself like this over to the B state. If we try to disturb it slightly from A and maybe put VI1 to here, it will find its way back to A. If we disturb it from B and put the VI1 over here, it will find its way back to B. If it is directly on C, so we call this circuit a bistable circuit because it has two stable states. But there is also, at this very center point, something called a metastable state, where if it manages to stay directly on C, it will stay there. However, even the slightest bit of a disturbance to either side, so if it goes ever so slightly to the side of C, it will then collapse into either the A or the B state, hence it's metastable. It won't go back to that state, but while it's in that state, it will stay there. Obviously, we've got plenty of thermal noise in our circuit because it's digital design, and we've got noise coming round from transistors all over the circuit, and so it won't stay in C for very long. It will eventually find its way back to either A or B if it does land in C, right? So it is a bistable circuit. It has that metastability, but it won't last for long, right? If we move this inverter down to here, right, we will find the it looks slightly different. It's the same circuit, we've just moved the inverter down to here, but this is the more common representation of this circuit, right? So we've got our two inverters cross-coupled, and we've got an out signal and a inverted out signal, right? So we've seen that it can hold its state. However, we also need to be able to change the state. There's two approaches to this. Either we cut our feedback loop somewhere, or we overpower our feedback loop, right? The cutting of the feedback loop is used in individual registers most of the time, whereas overpowering the feedback loop is used in SRAMs because it doesn't take as many transistors, right? We then had a look at cutting the feedback loop, and we saw, well, we can use a mux to do that. We can have a negative latch or a positive latch, where if we look at our positive latch, when our clock is high, our data is propagated to the output. When our clock is low, it's fed back round. In order for this to be regenerative, this mux needs to be a complementary CMOS mux. A transmission gate mux is not suitable here because it wouldn't be regenerative. However, we could use a transmission gate mux if we add regeneration through the bistable pair of inverters, right? So we have our pair of inverters as before. So there's your I1, the first inverter. There's I2, the second inverter. Or you could put it the other way around, doesn't matter. And then what we can see is that one part of our feedback loop just here can be cut off by a transmission gate, right? As we've got two transmission gates coupled to the other way round, this unit here ends up as a multiplexer, right? And so depending on whether our clock is high, in which case D propagates through to Q, or whether our clock is low, in which case Q is regenerated and propagated back to itself, we end up with either the transparent or hold condition, right? Latches, on the other hand, have a problem because they are transparent for such a long time, right? They're transparent for all the time they're high. The hold time is quite a hard constraint to deal with, right? We need to make sure that the contamination delay through our combinational logic is longer than the high time of the clock signal. Otherwise, we'll get new data coming through and propagating through the latch, right? We'll end up with an oscillator effectively. So it's very hard to satisfy the timing constraints on a latch. However, we have a cell that's a bit better than that. We have the flip-flop, which is only transparent for a very short time around the clock edge, right? And we implement this through the master-slave flip-flop, where you've got two latches, the master latch and the slave latch, right? And then these two latches, when working together, will only propagate on the positive edge of the clock. So let's say our D is changing very, very quickly, like this. Our QM, because this is a, let's just check which way round this is. Yeah, this is a negative latch, right? So our QM only goes transparent when the clock is low and holds its value while the clock is high. So we see, okay, our clock is low, our clock is high, it holds its value, clock is low, it oscillates, clock is high, holds its value, clock is low, oscillates. Then the other flip-flop is a positive latch. As a result, that value that's held on QM only gets propagated while the clock is high, right? So we see that clock is high at this point, meaning it's propagating the value of QM, but QM is stable. Then the clock goes low, so it's no longer propagating, even though QM is changing. The clock then goes high again, and it propagates this new value of QM, but QM, because it's now hot, because the master flip-flop is in its hold state, stays stable, and then the clock goes low again, and Q stays in its hold state, so it doesn't matter if QM is oscillating. This is how we create the flip-flop out of two latches, right? A negative latch, then a positive latch gives us a positive flip-flop. If we had a positive latch, then a negative latch, we would end up with a negative flip-flop, right? Obviously, we've seen that these latches can all individually be implemented as transmission gate multiplexer latches, and so the entire flip-flop can be implemented using transmission gates. And then we spent some time looking through the different paths, and we saw that if the clock is high, then D gets stopped here. If the clock is low, D propagates through to here but gets stopped here. And then when the clock goes high again, the value of D that was caught here propagates through to here, but D gets stopped here, so no more changes can propagate through. Right, and we saw all the different paths, right? So, and this is about where we got to, right? Give me a sec to just read through this because I've forgotten what was on this slide. Right. Yeah, so what this was saying is, given this circuit, what are the hold time and propagation, hold time, setup time, and propagation delay, right? So what we said was that the time before the rising edge of the clock, that D must be valid in order for it to propagate through to the output. So if we look back at our circuit, I'll get rid of some of these X's. So in order for D to get to Q, it needs to go through an inverter a transmission gate, an inverter, and another inverter, and it needs to get through there before this transmission gate closes off, right? So it needs to get through here, 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 and here before this transmission gate closes off in order for it to be latched and held in this feedback loop. Right? So you get 3 propagation delays of the inverter plus the propagation delay of a transmission gate. Right? So we need, specifically we need to get to here in order for it to work. Right? The hold time, so the propagation delay, so from the rising edge of the clock, how long before the value is available at Q? Well, we said that the value must get to here. So how long could it take to get to Q? Well, it needs to go through here, and it needs to go through here. So 1 transmission gate and 1 inverter. After it's gotten through those 2, it'll be available at Q. Absolutely guaranteed if we know it got just to here, which is the minimum point it can get to. Right? So TPD of the inverter, the delay of the inverter, plus TPD of the transmission gate. As for the hold time, the amount of time that D must be stable after the rising edge of the clock. So if we look back here, when we get the rising edge of the clock, this turns off very, very quickly. Very, very quickly. It turns off much faster than a signal at the same time coming through here, through here, through here, through here, and through here. Right? Because the delay from D to this critical point here is longer than the delay from the rising edge of the clock to this transmission gate turning off, we can say our hold time is 0. From the positive edge of the clock, we know that we don't need the data to change any later than that, right? If the data changes before the positive edge of the clock, it could maybe get through to here before this turns off. However, if it changes on the positive edge of the clock or afterwards, it will not get all the way through here before this is turned off. So our hold time, the time after the rising edge of the clock, is 0. Okay? Right? So let's have a look at some simulations of this. So this is based off a simulation done inside in Cadence. So you could, if you wanted, create this circuit in Cadence, in AMS, and do the simulations yourself. So here's a simulation of the setup time. So if we say, oh, we're going to change RD this long before the clock edge, we see that I2 goes low and QM goes high, right? So I2 is that middle node, right? If we set it at, so that was with 0.21 nanoseconds of T setup. So we said, okay, as long as it's 0.21 seconds, 0.21 nanoseconds before, it's fine. If we set it down to 0.20 nanoseconds, so the distance between the 50% point of D and the 50% point of clock is only 0.2 nanoseconds, we see that I2 drops down because of D, but it doesn't quite reach the 50% point. And then after the clock edge transitions, it regenerates itself back up to VDD. And similarly, QM, due to its voltage transfer characteristic, goes almost up to the 50% point, but doesn't quite make it there, and hence goes back down, and therefore Q doesn't keep the D on, doesn't stay high here, right? So yeah, Q stays high here, Q doesn't stay high despite the fact we put a 1 as the D, so it's failed, right? So it's important to make sure that you do not violate that hold time. So for this one, we can say that the setup time. For this one, we can say our setup time is 210 picoseconds, right? Because 200 picoseconds, we see that the flip-flop fails, right? So, we can do the same thing for our propagation delay. We'll put our D high, and we'll put our clock high, and then we can measure from the 50% point of the clock, how long does it take before our Q reaches its 50% point, right? And we can do the same thing for the falling edge of D, right? Notice how the 50% point on the rising edge is different from the 50% point on the falling edge here, right? We've got a low to high delay of 160 picoseconds and a high to low delay of 180 picoseconds due to the difference in electron hole mobility. Therefore, when you are evaluating your circuit, you should always take the worst case, right? Because if you have a situation where you are going from high to low, that's the delay you need to deal with, right? As you don't know what your data will be, you need to design all your circuits presuming that you're going from high to low, and it takes 180 picoseconds for your data to become valid on the output, right? And that is the end of the lecture slides. What is the time? We are at 1:47. So I am going to quickly show you the case for the hold time. So just like with the setup time, we have our clock going high at some point, and there's our 50% point. But this time, rather than having our D go high before and trying to measure the setup time, this time we're going to have our D go high after and measure the hold time, right? And we'll see what happens to our signals, right? So let's say our hold time equals, let's say 0.15 nanoseconds. Let's see what happens. Well, we see that our QM, which was originally high, so QM was originally high, goes down, it sort of bottoms out and then goes all the way down to 0. Meaning that our Q, what would be good? Let's use Q here. So here's our Q, meaning our Q ends up being pushed up to here and it goes high, right? So notice when our clock transitioned, our data was low, right? So we would expect for Q to end up as 0. Expected Q equals 0 because D equals 0 when we were at the rising edge of the clock, right? What we actually got was Q equals 1. So we failed our hold time, right? So this would be an example of something failing its hold time, and instead of storing this 0 that was actually on the data input at the correct time, it instead stored a 1, right? Conversely, let's set our hold time as 0.16 nanoseconds and look at what happens. Okay, so we've got our clock goes from 0 to VDD with our 50% point, and then we have our data goes high 0.16 nanoseconds afterwards, right? What do we see happen on the other signals? Well, we see that our QM, which was originally high, goes low, but it doesn't quite reach its crossover point, and it goes back to high again. And our Q, which was originally low, goes high, but it doesn't quite reach the crossover point, and then it returns back to a low value. We expected Q equals 0 since D equals 0 at the rising edge of the clock, and the result Q equals 0, so it passed. Therefore, we can say the hold time of this flip-flop is 0.16 nanoseconds, right? This is not the master-slave flip-flop, which you saw a few slides ago. This is some other flip-flop, but this is just showing how the setup time can operate, right? With a different style of flip-flop, maybe we've got a 0.16 nanosecond hold time, and if we violate that, if we change our data before the 0.16 nanoseconds, then our flip-flop will fail to keep the old piece of data that we wanted. Not that one. That one. Right? So here we only had it as 0.15, and it failed to maintain this 0. Okay? Right. Any questions? And I will quickly check what that one. I just need to check this one as well, just in case. Right. Okay. Is there anyone actually watching? So there are 2 viewers on YouTube. Right. Right. So are there any questions that people want to ask before we close down the main part of the lecture? Right. Can you explain how the hold time is 0 for the MSET implementation? Right, okay, so going back to here, so the main thing to remember here is that, click that as well. Right, so main thing to remember here is that we're saying from this positive edge of the clock, what time after that positive edge of the clock is D allowed to change, right? So the minimum will be 0, like the minimum ever possible would be 0. The maximum, well, depends on the exact paths, right? So let us take, so say this changes 0.1 nanoseconds after, right? And we'll say that this one turns off 0.3 nanoseconds after, right? This is all after the clock edge, right? We'll say that the propagation delay of this is 0.1 nanoseconds, and this one is 0.1 nanoseconds. This one is 0.1 nanoseconds, and the propagation delay of this is going to be 0.15 nanoseconds, let's say, right? So we've got all these gates before we get to here, right? So we say our D changes at time 0.1, right, here. At time 0.2, it gets to here. At time 0.35, it gets to here. At time 0.45, it gets to here. And at 0.55 nanoseconds, it gets to this point. At time 0.55 nanoseconds. This one turns off after 0.3 nanoseconds. So this one is already turned off, and that new value of D did not get through to here, meaning it can't disturb the output. Okay, so 0.1 nanoseconds we managed to keep the correct value of data. What if we say it's 0.0 nanoseconds, so directly on the same time as the clock edge transitioned? Well, this occurs at 0.1, this occurs at 0.25, this occurs at 0.35, this occurs at 0.45, and this transmission gate has still managed to turn off, right, before the data got to here, right? Unless you have a very, very slow transmission gate just here, because there is such a long path, that's not what I wanted, because there is such a long path to get all the way through here, round here, through here, and to here, because that path is so long, this transmission gate will have turned off well before the data gets here, and so our hold time is 0 from the clock edge, right?
Okay.
Theoretically, it could even be negative, but we just say 0 because negative hold times are a very odd thing to try and analyze. Okay?
Okay. Thank you, sir.
Right. On the other hand, obviously, because there is such a long path from here through to here, our setup time is actually a very long one. If we had a very different implementation where the path afterwards was quite, like where we had a short path to get to this point, and the transmission gate was quite, took a long time to turn off, then maybe we might have a 0 setup time but a long hold time. So it depends on these, on the equivalence between these paths.
Okay.
Right, any other questions quickly? No? Okay, in that case, 5.1.6. Right, so this is not a question. Right, I'm going to make this clear. You do not have to answer this question. This is optional in its entirety, because obviously this is one of the ones I said you don't need to complete. So we're looking at Lab 3, when it gets down there to question 5.1, part 6. And give me a moment to remember what it's saying. Implement a test bench to verify the functionality as well as the worst case high to low and low to high for Y. Ensure the load is 10 femtofarads. Right, and then it's saying sort out the like run all the simulations and populate table 2. Right, as for what the question was, just need to check it. For the minimum size inverter for the calculated delay of lab 3, for the minimum size inverter for the calculated without parasitics and simulated without parasitics is different. Yes. Okay. So, when you do your simulation, so you'll do your simulation and you'll get values for your minimum sized inverter, your minimum sized Y, and your custom sized Y, right? That the simulations will always include parasitics, right? That's fundamental. For the calculated value, you can calculate it without the parasitic capacitances, so you don't consider the C-int components, or you can calculate it with parasitic capacitances, so you do include the C-int components. So if we assume that our C-int is 1 femtofarad for a minimum sized inverter, and I'll just show you the inverter a sec. Right, so we've got our minimum sized inverter, 1, 1, like this, in and out, and our 10 femto. Without parasitics, we've got a 10 femtofarad load. Right, so we've got RNCL or RPCL, so 0.6 0.69, 0.69. With the parasitics, we've got a 12 femtofarad load. So we've got 0.69 Rn Cl plus 2C int, or 0.69 Rp Cl plus 2C int, right, for our delay. Right, AV extracted view. So AV underscore extracted. Oh yeah, okay. Yeah, sorry. So, sorry. I should not have called that parasitics. It should have been called intrinsic capacitances. Yes. So that was my mistake. It should be called intrinsic capacitances in the lab script. AV extracted gives you your parasitic capacitances, whereas the simulation gives you your intrinsic capacitances. Right, yes, I'm very sorry. So yeah, parasitics has to do with the wires, whereas the intrinsic capacitance is to do with the capacitance between the gate and the source, between the gate and the drain. I did those the wrong way around. That's the source, that's the drain. But so you've got a capacitance there, a capacitance there, you've got a capacitance there, capacitance there, a capacitance there. So that's all the intrinsic capacitances, whereas the parasitics are the wires themselves, right? So yes, that should have said intrinsic, and similarly somewhere further up in the lab script, I believe, where was it? There was another question that asks about it. I think it was, there was one that asked you to calculate, and it also said parasitics where it should say intrinsic. Okay. Unfortunately, this thing does not like scrolling today. It's probably this one, right? Yes. So this one, or it might be the next one. It says about parasitic capacitances. It should say intrinsics again, right? Right, okay, so that should answer your question, Spiros. Brilliant. Right, if we don't have any other questions, then I will end the stream here, okay? Right, okay. End the stream on YouTube.